Good morning, everyone, and welcome to our another set of video notes. Hopefully this isn't giving you flashbacks to your COVID years. Now, today what we're going to be doing is we are going to be taking notes on our last topic for Unit 1. This topic is how to use some new equations to talk about changing velocity. Up until now, we've only been talking about constant velocity in our math problems. We recently added more verbal descriptions and graphical descriptions of changing motion, also known as acceleration. However, now we're going to be tagging that math on. So, what we were used to is the equation x equals vt plus x0. We use this for any time we have constant motion. This equation had the variables x for distance, v, our constant velocity, so we just leave it as standard v. There's only one of them involved, so there's nothing else to it. There's t for time, and there's x0, our starting position. Now, we need to start talking about something different. In the real world, we change our speed. I mean, we travel at constant speed in the real world, right? We're going to set cruise control sometimes. But if you picture any journey, it almost always starts out at rest. So, with that in mind, when we have two different speeds, such as starting out at a stop sign at rest, we're going to call the first speed v1. Now, as we travel, our speeds are going to change. We'll end up at a different speed, v2. Right? You'll be at a stop sign, you'll speed up till you get to the speed limit. Then, once you're at the speed limit, you'll be going in constant motion. Now, it takes you some time to change your speed, during which you experience what's called an acceleration. Now, you're going to notice I will sometimes not have one of these boxes filled in. It's because generally our equations will always contain 4 variables, and then there will be one piece of information that doesn't work with the equation we're adding. For instance, this equation, v2 equals v1 plus a times t. Well, we use this equation when we don't have distance or care about the distance that we traveled. This is the way I think about it, and we'll look at this in a second. Now, it comes to mind for me just for a moment that we should probably define some of these variables before we talk about the equations that use them. So let's go with let's start here. Our initial velocity uses the symbol of v1 and the units of meters per second. This is our starting speed, our starting velocity. Whatever is at the start of the problem, however fast you're going, it's often 0. The next variable we have is our final velocity for a section of a problem. The symbol for that is v2. Units are also meters per second. And that's just our final velocity. Time remains t. The units remain seconds, and it's how long / how much time passes in the problem. If you hear us asking, how long does it take? We're talking about time. Next up, we have acceleration. The symbol for that's going to be A. And the units for that are meters per second squared. That's an easy one to make a mistake with, because now it looks a lot like the unit for velocity, but it has this squared on time. It's because it's how much your meters per second change every second. And that extra second in there means that it's squared on the bottom. So that tells you how much your speed changes every second. Last one we have here is x. We're going to leave x 0 out of these kind of problems simply because it complicates our variables a lot. So we have x, that's distance. Excuse me, I wrote the symbol by where the description of the variable might be. That's our distance traveled. The units for that remain meters. And this is how far you travel. All right. So, now that we've defined some of these variables, let's go back and learn more about our equations. Because right here we had one that doesn't have distance in it, and we don't care about distance in that case. Now we have to look to our next equation. This next equation, number 2, still has t, it has x in it, it has v1, and it has v2, but it doesn't have acceleration in it. Now, since acceleration tells us how much our speed changes by, I like to point out problems where we use this equation still have acceleration in them. We just don't care about a. We don't have a. I said it's not a given. That equation is x equals 1/2 v1 plus v2 times t. All right. Our next equation has a in it. It has x in it. It has v1 and it has v2. This equation doesn't have time in it. Equation's v2 squared equals v1 squared plus 2 times a times x. Now, I want to point out a common point of confusion for people. v2 squared and v1 squared are still just v2 and v1. We're just going to take whatever number we have for v1 and square that number. So we use this when we don't have time, and we don't care about t. All right, our last equation. You'll see a pattern here. This one has x, this one has a, this one has t, and it has v1. You'll notice a lot. We have an equation for that is missing like one of each variable except for v1. And that's okay. This way we have a bunch of different options as to when it comes to solving a problem. That last equation is x equals 1/2 at squared plus v1t. We use this when we don't care about v2. We haven't been asked to solve for it when we weren't given v2. All right, let's take a look at a couple examples of this. Now down here, we have a person. They're going at 2 meters per second. Well, if I'm riding my bike and I'm going 2 meters per second, that really sounds like a starting velocity to me. It sounds like the start of the problem. Oh, then they accelerate at a rate of 4 meters per second squared. So that's going to be our acceleration down here. Now, a good way to identify your accelerations in every problem is that acceleration is measured in meters per second squared. It's the only thing we're going to measure this year with that unit. So anytime you see meters per second squared, you know it's acceleration. Just like time here is the only unit measured in seconds. So our time is 2.54 seconds. We want to know what's the final velocity of our bike. So how fast we're going at the end. All right. Now let's look at how we use these equations to solve our problems. The way we're going to select an equation is by looking at what we do have and what we're looking for. The other way to look at it is we don't have x and we don't care about x. We weren't given it, we're not looking for it. That would mean we'd use equation number 1 right here. For reference in the classroom, these equations are all numbered. This is equation 0, 1, 2, 3, and 4. And we'll generally be referring to them as such. So, I don't have x, I don't care about x, that tells me I'll use equation 1. The other way I like to look at it is that I know v1, I know a, I know t, and I'm looking for v2. I need an equation with the 3 things I do know and the 1 thing I'm looking for. Still gets me to equation 1. We'll write our equation in with no numbers plugged in. Then we're just going to plug the numbers that we have into that equation. v2 equals 2 plus 4 times 2.54. Time to bust out that handy calculator. Now, 4 times 2.54 is going to give us 10.16. Add those together and we'll get 12.16 meters per second. There we go. Let's try another. We're going to have 3 practice problems on this page. All right. We have a train. Ooh, and this problem tends to be tricky for people, and I'll explain why. We have a train. It's increasing its velocity from 11 meters per second to 33 meters per second over a period of 20 seconds. We want to know how far did it travel during this acceleration burst. Now, a common misunderstanding people have with this problem is that they see that term acceleration burst and they think that we're going to be looking for acceleration. But that's not what we're asking for. We asked how far did it travel. Now, this is where it's really important that you're working your way through, writing down your variables as you go, and just sometimes pausing and rereading a question. In this case, we have v1, we have v2, we have t, and we're looking for x. That's going to take us to equation number 2. X equals 1/2 v1 plus v2 times t. Now we'll plug in our numbers. X equals 1/2, 11 plus 33 times 20. And now one thing I notice is when people write down more of their steps, it really helps them. So let's write down a lot of our steps along the way. 11 plus 33 gives us 44. Now we can do 1/2 times 22. They're all multiplied together, so we can go in any order we want with those. That's 11 times 44. The 1/2 of 22 is where we got that 11 from. Lastly, we'll take 11 times 44, and I'll bring my calculator into the game there just to make sure I don't make a mistake in my head. It's pretty early. X is 484 meters. All right, let's try another one. A rocket traveling at, and when we tell you you're traveling at a speed, that's going to commonly be a way that we are informing you of v1. So that rocket's going 88 meters per second, and it accelerates at 8 meters per second squared for a distance of 8,000 meters. What's the final velocity of that rocket? You're going to notice we're writing down our variables and the units that go with them as we work our way through. Now this one's going to be using equation 3. I know that because I'm looking for v2, I have v1, I have a, and I have x. So I'm missing time and I don't care about time. v2 squared equals v1 squared plus 2 times a times x. All right. v2 we still don't know, so we'll leave it as v2 squared. v1 will be 88 squared plus 2 times 8 times that 8,000 meters of distance. Maybe this is the second stage of a rocket firing up. Let's start simplifying. 88 squared is 7744. 2 times 8 times 8,000 is going to give us 128,000. Add those together. We're going to get V2 squared equals 135,744. Now, a common mistake people make is they think they're done right here. There's nothing more to add up. I have no more numbers to deal with. Ooh, we still have that squared. So let's take the square root of each side. And let's see what we're actually doing here. V2 is now traveling 368.4 meters per second. Yeah, I think this is the second stage of a rocket. It launched, it accelerated up to 8.8 meters per second, and then the next stage lit up, causing it to continue accelerating. Now it's really cruising. All right, next up, you're on your way to school. After waiting at a stoplight, ooh, if you're waiting at a stoplight, you're going 0 meters per second. So that's our initial velocity. Sometimes in physics, we're not going to give you a number with an actual number. We're instead going to reference something that's happening, and you'll then need to understand it. That is generally always going to be 0, but you're going to have to look at words sometimes to identify that you're starting at 0 or you're ending at 0. In this case, waiting at a stoplight, you weren't moving. Now we accelerate at 5 meters per second squared. It takes us 4 seconds to do that. We'd like to know how far did we travel in this time. Well, I have V1, I have A, I have T, and I'm looking for X. That tells me I'm going to use the equation X equals 1/2 AT squared plus V1T. The other way to look at it is, we don't have V2, and we don't care about V2. As we plug our numbers in, X equals 1/2 5 times 4 seconds squared. We're going to see that oftentimes a 0 as a starting position with this equation simplifies our work. Because now as we go into substitute, 1/2 of 5 is 2.5. 4 squared is 16. 0 times 4 is 0. That goes away. 2.5 times 16 is going to give us a distance of 40 meters. All right. We have 3 more problems to try out. And then you're going to have practice problems on the following pages on the exact same topic. Let's try these out together. We've taken away the scaffolding now, and this is what a lot of your problems will look like. The velocity of a car increases from 2 meters per second to 16 meters per second. V1 is 2 meters per second. V2 is 16 meters per second. It takes us 3.5 seconds to do this. What is the car's acceleration? All right. Well, in this case, I have V1, I have V2, I have T, and I'm looking for A. So if I went up and I looked at what I know, well, I'm going to have to use equation 1. It has both our velocities in it, and time, and the acceleration that we're looking for. We'll plug our numbers in. You're going to see that these equations are not always laid out so that the thing you're looking for is on the left. 16 is equal to 2 plus A times 3.5. Now we need to get A all by itself, so we're going to have to work backwards with our math. First thing I can do is I can subtract 2 from each side to get 14 equals A times 3.5. Once we've done that, I can undo my multiplication here with a little division by dividing each side by 3.5. 14 over 3.5 is going to give me an acceleration of 4 meters per second squared. All right. This is, by the way, exactly how you'd want to show your work on a test. The only thing you might do in that case as well is put a little box around your answer. That just helps us to find it when we're working through it. We grade you on your process, however. All right, let's try this next one. We have a bus traveling at 8.33 meters per second. It accelerates over a distance of 250 meters. Now this is where you want to be careful. We just used the term accelerates, but we gave you a distance. That again is because acceleration occurs whenever we change our speed, but we don't always care about the acceleration value or give it to you. This is one of those cases where we use the term accelerate, but we're not looking for acceleration and we don't care about acceleration. Alright, so it took a distance of 250 meters to accelerate. It reached a speed of 20 meters per second. How long does this take? Alright, let's check it out. Here we've got V1, V2, x, and t. We're going to be able to use our equation x equals 1/2 v1 plus v2 times t. Plug our numbers in. 250 equals 1/2 8.33 plus 20 times t. We'll just keep simplifying our math work. 8.33 plus 20 is 28.33. Half of that is going to be 14.165 times t. Next, we're going to undo that multiplication with a little division. We're going to find the time it took here. You see it took about 17.65 seconds for that bus to change its speed. Last problem out of our examples. Then you have some time to practice. An airplane must reach a speed of 71 meters per second for takeoff. Now, this one's a tricky one. I'll tell you that. This plane has to reach a speed of that. So if I need to end up reaching a speed, that tells me that that's the speed I need to be going at the end if I'm taking off. So that's actually V2. That's how fast I have to go in order to get the airflow over the wings that I need to take off. If the runway is 1,000 meters, what acceleration is needed? Ooh, it feels like we don't have enough information here. But I want you to just close your eyes and picture a plane sitting on the runway, waiting to take off. Needs to get to 71 meters per second. It's got 1,000 meters in front of it. And it's just sitting there, waiting, about to hit the throttle and rev up the engines, push some air, and start moving. But I'm waiting. So V1 is 0 meters per second. All right. Well, I have V2, I have V1, I have x, and I'm looking for a. I'm going to be able to use V2 squared equals V1 squared plus 2 times a times x. Plug our numbers in. And this is where this equation can get a little nicer. 0 squared is just going to be 0 later. All right, now we'll start simplifying. 71 squared is 5041. 0 squared is 0, so it goes away. 2 times 1,000 is 2,000 times our a. Let's get that 2,000 away from the a and find our answer. divide each side by 2,000 to undo that multiplication, and we'll find our acceleration is 2.5 meters per second squared. That's actually not that impressive of an acceleration. You'll find that a lot of modern electric vehicles, when you really push them, will have an acceleration close to like 7 meters per second squared. So our planes really are able to achieve a takeoff on that runway relatively easily. All right. If you have any questions, please don't hesitate to reach out to your physics teacher. I hope you have a great day and a good time getting your practice done. That again, that practice is on your following pages. We left the scaffolding on there for you. Have a great one.